Hello, welcome to Luka's Ludicrous Laboratory. My name is Luka Pickler, and today we will be investigating space-time, gravity, and all its dependence. So first we can observe this cloth, and this will represent space, the fabric of reality. Now, Einstein estimated that any object on space-time or in space-time will curve or dip in it, and this dip will get steeper and steeper and steeper the closer you get to the mass. Now, any other object will experience this pull at an increasing rate, which is because of the increasing steepness. Now, in reality, this mass also would experience the pull from this little marble, but it's small enough that it's not really noticeable. Now, an interesting thing to think about is this universe is two-dimensional, it's 2D, right? But it bends in the third dimension, the height. It only has width and depth, but it bends in downwards, which is height. So, by transitive property, our three-dimensional universe, when there is any mass in space-time, will bend in the fourth dimension, which we cannot perceive, us being mere three-dimensional beings, but it's an interesting thing to think about, and, it's cool. So, now that we know this, we can observe some more complicated things about matter and space-time, which, first thing we're going to talk about are orbits. Now, there are 4 types of orbits. The first and most rudimentary type of orbit is the parabolic orbit, which is easily done at home even. You just jump up, and when you land, you have successfully orbited the Earth parabolically. Whenever you jump up, or whenever, let's say, this marble jumps up, comes back down, it makes a perfect parabola. And no matter how you do it, your center of mass will always make a perfect parabola. And that technically is orbit and way to orbit the Earth. And you can even get very high up into space with a parabolic orbit, but you can't stay in space. In order to stay in space, you have to orbit the Earth in a different way. Now, this brings us into elliptical orbits. Elliptical orbits are different from parabolic orbits in the way that they come up, but in order to stay up there, they get up really high, then they start going sideways really fast. So they're always falling, but they're falling sideways, which is interesting. So, elliptical orbit can be represented by throwing this marble sideways. And you can see how the marble will orbit the mass until it comes to a rest, which in space that would not happen because there is no friction in space. But in my setup, there is friction that will eventually slow this marble down faster than if it would in space. In space, it would continue forever, like our Earth is doing around the sun. Good thing that doesn't deteriorate, or else we'd all be dead. But we can see how it orbits, right? And it can orbit in both directions. There's no Coriolis effect here. But that is how an elliptical orbit works. And there's one more thing about it. An elliptical orbit will have an aphelion and a perihelion. And these are just fancy words for the 2 points that are closest and farthest. So the points are when they're closest and farthest away from the mass they're orbiting. So the perihelion is when it's closest, and the aphelion is when it's farthest away. So notice how when the mass reaches the perihelion, it's going a lot faster than when it's at the aphelion. At the aphelion, it's slowed down, then it zooms in closely for the perihelion, and that's because it is steeper at the perihelion, so it'll go faster, right? And at the aphelion, it's slower because it's not as steep. The curvature is not as, not as steep. So that's one thing to keep in mind about elliptical orbits. Now, the third type of orbit, the circular orbit, is more of a concept than an actual orbit because it is the same thing as an elliptical orbit, except that it has no perihelion and aphelion because it's perfectly circular. It will always be the same distance away from the mass, wherever it is. And this has the same properties as an elliptical orbit, except that it's really hard to achieve. You have to be, it's basically theoretical, so there's not much else to talk about that. You basically still have to go up really high and start going sideways really fast. And that's actually the reason why rockets are so big. It doesn't take that much lift to get you into space. The reason why rockets are massive are because they have to get into orbit, and in order to do that, you have to go sideways really fast. This is why you have those long burns, right? Because you can actually send a model rocket up to space. You can see videos of that on YouTube. But anyway, the last type of orbit is a hyperbolic orbit, and this is the strangest orbit of them all because it's not how we commonly perceive an orbit, because this orbit does not stay around the mass. You will leave it entirely. Right? A hyperbolic orbit uses its own mass and the gravitational force of the mass to slingshot its way out of orbit, right? So notice how I'm not throwing this in a straight line. I throw it in a curved line. And if I throw it hard enough, the mass leaves altogether. It slingshots using the force, and it kind of pulls it and throws it using centripetal force, and that throws it away. And off it is now to different solar systems, or maybe not, because space is vast and the chance of hitting a solar system is very, very close to zero. Anyway, that's how a hyperbolic orbit works. Right? You have to basically, if you're doing this from Earth, you have to go up really high, sideways really fast, and then keep on going sideways really, really fast until you eventually leave. Or you can just keep on going up, 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 up until you finally leave. They both will work. Now that we know the rudimentary parts of orbits and space-time and gravity, we can talk about some crazier things. So, one thing I'd like to talk to you about is how moons can orbit a planet which can orbit a sun. Now this is hard to model using my materials, but sometimes it works, sometimes it doesn't. Now, we'll reassign this weight as a sun now, and the rubber ball will be the moon. And this will be, the rubber ball will be the sun, or the Earth, and this will be the moon, right? That's the sun, Earth, moon. There we go. Now, we can notice that the Earth will orbit around the sun, no problem, right? And now if we put the moon close to the Earth, we can maybe see if we can get it to orbit around the Earth. See, it works a little bit. Yeah, it's orbiting around the Earth, actually. It looks like it's staying still, but that's because the Earth is also moving, which is pretty interesting. So now we'll try it again. Oh, that time. Well, you get the idea. It's very interesting how it does not very noticeable, but this small mass can still produce a large enough curvature to make something else orbit around it too. That's how the moon is orbiting us. Now, time for something really more drastic, and now we're talking about black holes. A black hole is a very interesting anomaly that happens when a very, very large and dense star becomes a supernova, right, which usually will result in a neutron star, which is also very dense and very catastrophic if it ever comes our way. Makes us miss dinner, but really big stars, like hypergiants, will turn into black holes when they collapse. And that is when all the mass is compressed into such a tiny, tiny, tiny area that it shatters reality, breaks it, punctures a hole in it. If I were to puncture the hole in this fabric, then I would have created a black hole in my temporary universe, right? So you can imagine when something goes infinitely deep until it punctures it, you can't. Once object falls out, it literally fell out of reality. It does not exist anymore. It's gone forever because we broke reality. Oops. Anyway, so that is called the event horizon. Once you pass that point, you're not coming back out. Even light cannot escape that point, which I'm sure you already know. Now, another thing about black holes, a misconception, is that you have to have a lot of mass to have a black hole. That is not true. Anything can become a black hole if compressed small enough. The Earth could become a black hole if it was compressed roughly to about 2 kilometers in radius, and then the mass would have compressed so much that it would break the point of reality. And I can model this by saying this quote-unquote sun is held up by space-time, right? It does create the characteristic curvature, but if I were to compress all this mass into the size of a grain of sand, chances are that grain of sand would pass right through the porous cloth, because this is just cloth, it's not metal, right? And then I would have created a black hole. So therefore, all you have to do is get any mass, make it really small, and eventually it will create a black hole, which is an interesting theory to talk about. That's all I have time for today, folks. Thank you for joining me. I am Luka Pickler, and this has been the first and probably only episode of Luka's Ludicrous Experiments, or Luka's Ludicrous Laboratory. Thank you very much for joining, and I won't see you next time.